Hi, I'm Kiara. Here's my ID. Here we go. All right. Okay, first we're going to start off with the part 2 of the presentation, which was determining if certain compounds were identical to an original molecule. So about the original molecule, I was very particular about having a particular substituent match a color, because this is really confusing for me and it helped me a little bit. But I still have those sticky tabs that you wanted us to use. I just wanted to let you know that I really relied on color on this one because it's hard. Okay, so white is a hydrogen. In the original molecule, we have that kind of coming out towards you. For the OH, I chose brown, so I'll put a little OH sticker there. Hopefully you can read it. Coming off, going away. And then we have the CHO, which is red. And I have that at the top, a bit over there. And then I have the CH3, which is green. And it's kind of in the same plane, but it's kind of going away from here. Okay. So here, if you're looking at it, the OH takes priority, and then the CHO on the top, and then the CH3 here at the bottom. So you're looking at a counterclockwise rotation. However, the hydrogen is facing towards you, which means it needs a switch because hydrogen is supposed to be facing away. So it's actually really a clockwise rotation, which makes it an R. So the original molecule is an R. Sorry, my computer. Don't go to sleep, computer. Okay. So the next one, or that was the original molecule. The A, the one that we're comparing it to, is actually an enantiomer of the original. I actually built a separate model for it because it was that confusing where I needed to make my way through this. So I know you wanted us to use the stickies and kind of just move them around. And I kind of do, but it really helped me to build another one. And it actually helped me realize more that they're enantiomers because they're mirror images of each other and they're not superimposable. So it answered my question by having to build another one because the first molecule wouldn't fit. Anyway, okay, so we've got the H going away. The CHO, which is red, is coming towards. Okay, CH3, which is green, is on top. And then the OH is coming out to the side. OH, brown, OH, CH3, green, on top. All right, so OH takes priority. OH will then go to the CHO and then to the CH3. So you're looking at a counterclockwise rotation, which is an S, and it stays because the hydrogen is pointing away. So we're good. It's the first one, the A compared molecule, is an enantiomer and it's an S rotation. Okay, the next one ended up being identical to the original one, so we're going back to the other one. In this one, the hydrogen is going away, and the OH, which is brown, is coming towards, and the CH3 is hanging out straight up, CH3, and the CHO, the CHO is also hanging out on the same plane. Okay, so here you've got the OH takes priority, then to the CHO, and then to the CH3. So going this way, you've got a clockwise rotation, and that makes it an R. The hydrogen is going away, so we're good. So the B comparing molecule to the original is an identical molecule, and it is clockwise rotation, which makes it R. Okay, I'm going to go back to the enantiomer. Okay, so C, for the comparison, is an enantiomer. I had to go back to my enantiomer molecule. We've got the hydrogen coming towards, and the OH going away, and here's your OH. Brown OH going away. Okay. And the CH3s kind of come off to the side in the same plane. And then we've got the CHO, the red CHO, going this way. Okay. So for this one, you've got the OH takes priority, then the CHO, then the CH3. So you're moving in a, I'm so sorry you couldn't see that. Good Lord. Okay. All right, so you've got this, the OH takes priority, and then the CHO, and then the CH3. So it goes around in a clockwise direction. But note that the hydrogen is coming out towards you, which means you got to swap it. So it would be a counterclockwise rotation, which is an S. So the C is an enantiomer with an S rotation. Okay. The last part of the video presentation is polarimetry. So, how could you know the molecules are optically active just by looking at the structure? So if you look at the structure of the molecules, if it's chiral, it's going to be optically active. So you can tell, looking at the structure on paper, whether you should get a result by putting that particular solution into a polarimeter. Okay, scoot my chair up. So the way that I put the stuff together is you have a source of light, a candle. You take a beaker and you put it upside down. Okay, really important you have your the polar filter paper, I guess. And then something I guess you should probably note about the paper first. So when you hold it up, and you hold it a certain way where the papers are overlapped, sometimes it can be really, really dark like this. So that's an extinction point. If you rotate one of the films 100 maybe 90 degrees, there we go. It's clearer, you can kind of see through it. But if you, I know it's hard to tell in the video, but there you can see it's darker now. So the very darkest where you can't see any light at all through it, that's an extinction point. So I know just practicing that, like, okay, it's dark now, it's the extinction point. If I rotate one of the sheets, so I can see through it now, and then I rotate it again 180 degrees, it hits the next extinction point. So I know that without anything in the middle of it, if I rotate one of the films 180 degrees, I'll hit an extinction point. So the way that we use measure in the polarimeter is we put a piece of polar film there, put it between the beakers. Okay, and the plan was to take a liquid, dextrose, alanine, fructose, and you put the liquid into the beaker. So there you have the liquid in the beaker, and then you put the polarizing film over. And so what you should expect to see is an extinction point. And what you want to do is turn the film until you see another extinction point. It should go dark again. The reason for that is the light's coming through as it's hitting the molecules will bend the light, so it changes what you see in terms of extinction point when it goes dark again, because it's bending the light. And then you'll see, depending on the liquid in there, you'll see a difference in how much it's, you'll see a difference in the degree of rotation. So let's see, indicate how you found the extinction point. Tell me your results. Okay, so in my results, I kind of was not happy because I don't think I did it right for the first two. I understand that, when you're using a polarimeter like this, the amount of liquid you pour in matters, which is why we measured the height of the liquid, because if you have more liquid in there, there's more molecules in there to bend the light. If you have a different concentration of liquid, or solution to a different concentration of solution, that matters too, because if it's a higher concentration, then you have more molecules to bend the light, which will affect your results. So I know that there's some places, that they gave us a very specific, what's it called? A specific rotation, or how many degrees that you would turn it until you see an extinction point again. And I understand that that's, it's measurable. It's like it's a what's it called? It's a not a variable. Like, once you calculate out all of the variables, including the concentration and the amount of liquid that you have in there, that you have, a specified rotation. So I know that the point of the lab was kind of to calculate our own rotation and see how far off we were. And that's kind of where I got frustrated. So, I'll show you my results. These are my results. So, when I did the alanine and the dextrose, I got really irritated because I noticed that my observation of extinction point was the same, like almost the same to 180. And really, it's supposed to be different. Like, 180 is when there's nothing in between the two polarizing films. So by putting that stuff in there, it should have bent the light, or putting the liquid in between the two polarizing films, it should have bent the light. So I should have got something different than 180, like less or more, something different. That's, you know, then I would be able to measure it. But I went with the numbers, and I kind of like, I tried to retest and retest. I kept the numbers and went with them just to drive on. But I knew they were wrong, because when you come out to the error, like my alanine is 775% error, and my dextrose is like 500% error. That's way too much error. Like it's wrong. I did something wrong. And I was irritated because like I let the solution sit for like a day and a half, you know, shaking it, just like the solution we were using in the next lab. Like I let it sit. It should be concentrated enough. I can only say that maybe I set the polarizing film up wrong or whatever. But I can say that it's good that in the fructose, when I tested it, I definitely got a different extinction point than, you know, a normal 180 turn. And it was actually a negative 22, so turning it the other way, which I was like, oh, thank gosh, like this is different than 180. I'm supposed to get different results. This is fantastic. So I got the negative 22, and then when I figured out the percentage of error, I got a 35%, which I'll take it, you know, over the 500 and the 775. So at least one of my chemicals came out correctly. There are quite a few ways where I could have gone wrong. Maybe I did this, I don't know how I did the solution wrong, you just add water. But maybe the polarizing film wasn't right, or I had it flipped the wrong way. It's possible, but one of them came out. So I know theoretically how it's supposed to work. I understand all of that. Let's see if there's anything else that I need to include here. Demonstration apparatus, indicate how you found the extinction point, the results. You know I'm supposed to include my calculations. I know you saw my answers. I guess if you wanted to see the calculations, here they are. Yeah. So, yeah, I'm kind of sad that the first two didn't come out, but thank goodness the fructose came out correctly, and yeah, gave me an opportunity to have numbers that made sense, and you know, validate the concepts in the lab. All right. Well, I think that was it. Hopefully I explained everything I was supposed to. Yeah, organic chemistry. It's tough. It's tough. Thanks.